How does a static analyzer work? Good question. So, this is the entry point, or the main entry point. Analyze RC critical sections in file. And we give it a file path, which is a string. Maybe this is not the right form for server stuff. Well, I'm familiar with like that kind of thing. I just didn't know the specific terms or technologies because I don't keep up to date on all that crap. Like computer's a computer, right? But I need to like I used S3, not S3, EC2 to build GCC on a 50 bazillion core machine because I just got this crappy laptop here with 4 cores and thermal throttling. So I could build GCC from scratch in like 10 minutes on a beefy Amazon machine. I did that on stream for a while. I find it interesting that the programmer world is so strictly divided between backend and front. It's not divided. It's not divided. I think a lot of people specialize because that's where their interest is. Like, if you like making visual stuff, like this thing, if you like making little chat visually doodads like this, then you're going to do one type of programming. If you're doing like analyzing files, reading assembly out of it, and doing crap, you have a totally different hat on. A totally different set of skills. Not totally different set of, a very different set of skills. So it kind of makes sense that people with similar skill sets kind of gravitate toward GUI stuff and web stuff like front end, and other skills they gravitate towards server-oriented software. And some people go through programming language and batch software, and like they make their own little clicks, you know. I think it makes total sense. But there's some people that transcend all that, like me. Though I don't go into ML and AI, that's like another little click. So I'm in a few clicks, but not the ML click. I feel full stack is extremely common for web stuff, and that's only web stuff. Yeah, full stack is a stupid term. Because it's not full stack nothing. Would my distributed JSON file database turn someone like you on? Probably not, because it's JSON. Why not ASN1? Over HTTP across a cluster of guaranteed uniqueness and DNS round robin for 100% read time, uptime. Make. I don't know what I'm looking at. I don't want to play with it. What is stacks? Oh, stacks are, I don't know, it's like a marketing term. It's like a made up, doesn't really mean anything. It's like, it's kind of like concept art. Concept art is a very vague, nebulous thing. How is it different from the real art? Or, like, I guess it's where it is in the process. I don't know, I'm trying to relate it to something a UI designer might be familiar with. I guess it's like interior design versus UI design. They're both like design. They need design mindsets, like artistic design mindsets. But you're manipulating very different kinds of things. So front end and back end and full stack are like, front end you could say is the interior design of your store, and back end could be the UI of your apps, and full stack means you could do both. I mean, I don't know, it's kind of vague, but try to relate it. Failed, but oh well. So you prefer XML. Why do you have JSON anything? I don't know. Kissing wizards. Oh no. Oh no. Oh no. What is this? Oh, okay. I thought you were going to have me in Last Miles. But now I just gave you an idea. Stack is like stack of knowledge. Sure. Wait, do you consider database to be separate from backend? I don't know anyone who's said that. I know you can do it fiber lights. Didn't say you should. Just because you can doesn't mean you should. Network stack. Yeah. People hiring do, yep. That's weird. I have not heard that, but no, you did not miss an XML rant. I can be the assistant. The slave. Anyway, VJ, are you there? Because I was going to explain how my static analyzer works. Because VJ was asking. But if VJ ain't here, I ain't going to explain it because no one else deserves it. Solution stack? We want full stack dev with knowledge of SQL for the database. Okay. Oh. I like that definition. I like this definition of software stack. That's a... I don't know why I didn't go to Wikipedia or the Google, but that's a good Bao Ki. Thanks for bringing this up. That's better than whatever poop I was speaking. Vic J, are you like driving or something? What is going on? So full stack would imply you're touching all these things. But I bet you no one who calls themselves a full stack developer touches all of these things. Anyway. Whoops. No. Alright. So, this is my static analyzer. It's all right here. It's only, I don't know, 30 lines. Not really. So we initialize libelf. Libelf is another project, and for some reason you need to initialize it. I don't know why. Anyway. Then we open this file as read-only. It's a file path, opening the file. We check if it's valid. If it's not valid, then we failed to open it, so we throw an error. Whatever, error handling. Then we call elf handle begin. So that's tied. This is elf handle is a libelf thing. So now we're saying, hey, libelf, take this elf file, this like bucket of bytes, and begin. Like start loading up the juices. Loading up the juice. What does that mean? And say we're gonna read it. Instead, we're not gonna write an elf file. We're gonna read it. So an elf file is an executable. In this case, is an executable. So I guess I didn't build it. I don't have that right now. Well, I don't know why I'm building this. File. So, like, we have this program, and if we run file on it to get information about what it is, it's an elf file. That's just like on Linux, that's just an executable, just a program that you can make and then run. You're a lamp. I only code machine assembly. Lamp is too slow. Yeah. I'm with you, bud. You can't just JSON and not give an alternative. I did give an alternative. I said ASN1. All job offers here want lamps, so I pursue that career. Yeah. Are random numbers in computers really random? Is anything really random? Is the world deterministic? What is random? Random means you can't guess what it is. So, well, not you can't guess what it is. Nobody can guess what it is. So if nobody can guess what it is, then it's random. So it's really, is your computer guessable? And the answer is, I don't know. Maybe somebody eventually will guess the numbers. Example of my UI. Oh. Network connection terminated. Report a bug. Menu. That's cool. I like the styling here, like these little doodads you got on the corners. It's nice. And you got this like dip here. That's cool. I'm digging that. Yeah, if your computer goes in the back alley and gets some numbers, it's probably random. Anyway, so now we've initialized libelf and we told libelf to load this file as given by the file path. So when you run your check rseek, well, let's finish building this. Just cuz. Feedback placeholder. Well, I didn't want to read anything. You should build blockade to make players pay for it. The reason they're going to pay and the way they're going to pay lights is this. Players owe you money. $58 billion of microtransactions a year. The blockade will cost 10 billion blockades a year. That's what it's going to cost. It's going to be a powerful blockade. It's going to cost 10 billion. I like it. I was joking about ASN1. And so we give the thing a file name, and it does stuff with it. Here we didn't have a file. The file didn't exist, so it threw an error. And here it's complaining further on. We can give it a not elf file, and apparently it just chugs along. Alright, let's continue with this function. We create an analysis, and that's just that's like a place to shove analysis results in. Make an empty analysis so it doesn't have any issues in it. Then we parse rseek descriptors. What does that mean? Well, if we don't get anything out, then we report this problem that we got no rseek descriptors. And hey, what do you know? That's what's happening right here. It says section missing or contains no descriptors. So this string diagnostic is coming from this problem here. I can totally diss JSON without getting an alternative. It's my stream. Alright, goodbye, fiber lights. So what is parse rseek descriptors doing? Well, there's this helper function, but the real meat is down here. So we take this elf file, and then we loop over all the sections. And if you're familiar with elf files, then you know what that means, but if you're not, let's look at an elf file. Let's use readelf to tell us about the elf file. And it gives us details about the sections. So this loop over here is going to go through each of these little sections. Doop, 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 doop. And there's 39 of them, 0 to 38. What it's doing is it's getting the section name of that section. So the name, each section has a name. This first one is empty for some reason. This one's called .interp. This one's called note whatever. This one's called hash. So it's getting the section name, comparing it to rseek descriptor section name. That's a constant for data x86 trace rseek. So in this file, we don't got any. We don't got any data x86 rseek, whatever. So in our particular file, this will never be true. So then we just return an empty vector. And that's why down here we get this problem printed. Now let's look at the other case where we do got a thingy. We do have that section, because that's where the magic starts happening. The heck? Humans can't read binary. Who cares about humans? YAML is really slow. Slower than JSON. Okay, so let's run it on a thing that has stuff in it. So this is printing out nothing, which, I mean, is different than what it was before. So that means there's at least one of these descriptor thingies, which means we must have that section. So let's look at readelf's output again. And for some reason, readelf truncates the name. So this really should be like the EQ here, but it doesn't put it there. But it's there with the full name. So there's this entry, this section. It exists in this file. So we go inside this if. This if is like, yep, good to go. So let's do this crap. So we get the address of the section. That would be this thing. So this table, the section table has some header things. And it's weird because it's split up across multiple lines. So the top left thing is the name. The next thing over is the type. The type is prog bits. The next thing over is the address. The address here is 6B2DD0. That's some hex number. So this guy is pulling out the address. And then we get the section data. So really, the sections are slices of the file. So well, at least the things that say prog bits definitely are slices of the file. So they contain some binary data. And that's the offset. This tells us where that data starts inside of the ELF file. And size tells us how many bytes there are in the file that are corresponding to that section. So what section data does is it takes that data out of the file. It's not really important how it does that. And then we load up some binary parser thing, which whatever, and we give it the bytes that we just pulled from the section data. So we're going to start parsing the section data. So we're going to parse the data out of this data cxx trace rseek section. So while we have data still in the parser, we call parse descriptor. So what does parse descriptor does? Parse descriptor parses a 4-byte unsigned little endian integer and stores that in version. Parses another 4-byte thingy and stores that in flags. Parses an 8-byte thingy, stores that here. Parses another thing, parses another thing. So they're just parsing out some data from the section. So the section is just a series of bytes, and we're interpreting some of those bytes as meaning certain things, certain special fields. Okay, we'll take a look at that later. And then we're just accumulating them in this descriptors vector. So now we got a vector. Back to our caller, descriptors is a vector that contains a bunch of these parsed things that we pulled out of this section. What is auto in C++? It's a it's making a variable here. So this is as if I wrote sc vector parsed rseek descriptor, but auto is shorthand. So it looks at auto. Look at the thing on the right hand side of this equals. Look at its type, and then basically it'll replace the word auto with that type. What the heck just happened there? It'll replace the word auto with that type. And if we go up here, the return type of this function, so if you call this function the return type, the type you get out is a vector of parsed rseek descriptor. So auto is just doing the shorthand, but it doesn't mean Doesn't have any. Yeah, that's the gist of it. There's like a bunch of details to go into it, but because it's C++. Is it hard to read other people's code? Do I need to make the text bigger? It could be I wrote shitty code. Definitely possible. Or maybe I'm using a color scheme that you're not used to. I don't know. You still following me, VJ? So now we have some descriptors, and now they're not empty, so we're not giving that no descriptor problem. Because we're skipping over these lines of code, because descriptors contains at least one thing. Because the data, the section exists, first of all, and the data, like the size, is, you know, pretty substantial. It's like a kilobyte or something. I don't know. Less than a kilobyte. Yeah, the / operator, readable. If there are no descriptors. If this makes it more readable, then you need to be shot. Loop over the descriptors. Should I comment each, like, and if? Add the problem. You like those? As to the lines of code, and Bill Gates says measuring programs. So you're saying I should have these on their own line, so my program is more complete? There you go. Empty is a function on the on vector, and descriptors is a vector. So we can go up to the docs for vector, and it has a function, a member function called empty. Checks if the container has no elements. It returns true if the container is empty, false otherwise. It's actually saying the opposite. Measuring aircraft building progress by weight. Well, doesn't more weight mean it's more done? Therefore, more lines is more done? According to Bill G. Anyway, now that we have some descriptors, this code, as the comment helpfully describes, we're looping over them. Let me check if it's complete. Complete means, like, maybe up here, where are we? Where was it? Up here. Maybe we tried to parse 8 bytes, but there was only 3 bytes remaining. If there's only 3 bytes remaining, then this gets set to null. So is complete will see if any of those things are null, which means we didn't parse anything. If anything is like incomplete, then we report that as an issue. That rarely comes up. That's just another sanity check. Why does C++ developers die early? Because of all the STDs. Oh dear. I think Bill's being sarcastic. I think maybe it's a misquote, but... Okay. So we did that check. That's not really important. Then we build this data thingy. This thing is just going to be a way for us to pass some common things around between some layers of shmoo. But the first thing we do is the first real thing we do is we call function containing address. What are we doing here? And we give it the start address. So from the critical section, the start address, let me highlight it for you. So start address up here, start address down here. Critical section up here, critical section down here. So we're taking the RSeek descriptor start IP and which is the same as start address, and we're giving that to add function containing address. So what is a start IP? Start IP is like something we parsed out of this thing. Let's look at some assembly in a test just for a small example. So here's some example assembly which would create, like you would use an assembler to create an ELF file from this code. So this says we got an we're making a new section called data x86 RSeek, x86 trace RSeek. That's the thing our program is analyzing. We give some other crap which isn't important. We align it, not important, that's not important. So here's the fields. So here's a 4-byte thing, a 4-byte thing, an 8-byte thing, 8-byte thing, 8-byte thing. So that's similar to our, here we were parsing a 4-byte thing, a 4-byte thing, 8-byte thing, 8-byte thing, 8-byte thing. 44888. Long is 44, quad is 888. So those are corresponding fields. So what is a start IP? Start IP is the first 8, so the first quad. And here, the first quad is dot start. What is dot start? Dot start is a label referring to this thing down here. So dot starts will be the address of this code. And here the comment helpfully says that the address in this case would be whatever the heck this is. So now that we know roughly what start IP is, down here, when we're calling function containing address, what do you think function containing address does? I guess we'll look at what it does. Well, it's not in this file. So let's, I don't know what I just wrote to. Oh, I wrote all my beautiful comments, didn't I? Where is it defined? So elf function, so this is a function containing address. We're like username and password. We need a relation. No. Let's increment ourselves? What are you talking about? So this thing creates a struct. Ugh, oh, this is ugly. Basically, what it does is there's another part of the ELF file called the symbol table. It enumerates symbols, goes through each of those entries, and calls our little lambda function. So it's like a for loop. So let's look at an example of the symbol table. Actually, let's look at this program. Let me let's assemble that and run our analyzer on it. Or read elf it. Where'd it go? Here it is. So we're going to look at that just so we have a consistent example. So there's a readelf can also tell us the symbol table. So here's a symbol table, a representation of the symbol table, all that crap. So what is this code doing? First, it gets the type of the symbol and sees if it's a func. And if it's not a func, we give up. So that's looking at the type thing. So we got no type, section, file, object, no type, blah, blah, blah. We're still not at func. Hey, we got some funcs. So the first symbol it would see and continue with is this one, number 28. So what else does it do? It says address is within symbol. So that looks at the value of the symbol. So what is the value? Well, the value, the value column is this. It's also in hex. So it's going to look at, in this case, 510. What does it do? It compares it with address. What is address? Address is our parameter, our function parameter, for function containing address. Over here, that parameter was a start address. And remember that start address was 7F801. So that, the value is definitely less than that address. So then we look at this and we see, is the address less than the value plus the size? What is the size? Size is 0. So it's definitely not going to be that. So it's going to, because it's not, the address is not within that symbol, it's not within the beginning end, it's going to skip that symbol. So let's look for a symbol where, what's the thing we're looking for? We're looking for this. Looking for that. Oops. For func, this has to be a func, right? That was the first check. So we're looking through the symbol table. That's a func, that's a func. Let's highlight all the funcs. Oh, this one looks interesting. Well, do these line up? Hey, they look about right. So this is less than this, and this is less than this plus this. So it looks like this address is within this function so far. So that for that symbol, it'll keep going. Then we see function symbol has value. Function symbol is up here. It's an optional. This just checks if there's multiple functions. So let's skip over that for now. But now that we have the symbol, we're gonna stash that in the function symbol variable, so we can remember it later. Let's worry about that later. If we don't find a symbol, we give up. We throw an exception. We didn't find nothing. Remember, this function is called function containing address. So there's nothing that contains the address, then we don't have a function that we can return. So we gotta throw, or crash, or do something. Here we get the function name. Now what is this stuff doing? Elf stir putter. Function symbol st name, function symbol name, string table section index. Ugh. Basically, it's doing the work that readelf is doing for us. It's getting this column, the name column. So the name is my rseek function with an underscore in front of it, just because underscores are fun. Because this is the entry. This is the big money that we found, right? So function name will be that string for this stuff. Oh, it holds a lot of strings. Strings for days. So if you run strip on a program, on an ELF file, it's going to delete a bunch of those strings. And you'll see the file shrink quite a bit. Well, let's do that. Let's do that. Strip-o stripped. Well, actually didn't. Why the heck is this 2 megabytes? It's 2 megabytes? I don't know how the heck it happened to be 2 megabytes. Well, the stripped version cut out like almost 2 kilobytes. So about 2 kilobytes of strings for this program. This like assembly program, which I don't know how it's so huge in the binary. It's crazy. Anyway, this is the function name, right, that we pull out of here. And if we don't get a function name, put question marks. Why not? And then we do function from symbol. What is function from symbol? Doesn't matter. Point is, we found the symbol, and now we know my rseek function is what we're talking about. Now, if we go to the assembly code, you'll see my rseek function right there, and this is the start of the function. And you'll notice this address is the same as this address, so it's all consistent. And we say that the type of it is a function, which is why this column says func and not something else. Yeah, 2,000 letters from sad children who aren't getting their presents because we deleted all the letters. So yeah, that's function containing address. I mean, there's more details I glossed over, but we're taking it like medium speed here. Now, this could throw an exception, so we're catching that exception and reporting that as an issue. But let's not worry about that. So if we don't get a function, we stop. But let's say we do get a function. Then we call analyze rseek critical section. So this is where the real work starts. Now I've done some setup work to find our bearings, to find the function that we want to analyze. So now we're going to actually analyze stuff. So we're going over here. Create an rseek analyzer. That doesn't do anything yet. That just sets up an analyzer. We look at the function we got that we pulled out from function containing address, and we look at its instruction bytes, its size. If its size is 0, or if it doesn't have any bytes in it, we say, hey, we got an empty function. We are not in that case right now, so we're going to go down here to these analysis phases. So first we analyze the function instructions, then we analyze the abort signature, then we analyze address bounds. The more interesting stuff happens in analyze function addresses. The rest of this stuff is mostly like, so we have this descriptor up here. If these numbers were like totally out of whack, then that's what the other functions are checking. But we want to check analyze function instructions is more likely to have interesting stuff. You just got out of school for winter break. Best way is practice C++ on your own. Why on your own? Why do you want to do C++ on your own? Why not do C++ with other people? I think you'll probably have more fun doing it with other people. You can build better, bigger things with other people. So it'll be more interesting, and you'll solve more challenges that way. So work with somebody else. Probably a classmate, but maybe there's some friend you have that didn't take the class, but they know C++ well enough. You still have Vic J, or am I talking to myself and 32 other losers who don't have anything to better? They don't have anything to do except watch me on Twitch. Maybe I'm in a background tab and I'm muted or something. I don't know. Vic J, give me a heartbeat. Am I explaining this right? Am I explaining it well? Am I too rambly? Should I gloss over some things? Oh, so you're not really watching. Don't have friends that are fellow coworkers. All by yourself. What about your classmates? Been writing C++ for a year and a half at work, and I'm feeling like I'm never going to stop learning it. Yep. That's one cool thing about C++ is you're always learning new things. I don't care about you. This is how we are. I care about Vic J. Vic J sounded like they wanted to learn about this stuff. I mean, you can go on without him. We don't need Vic J where we're going. But it'd be nice to have them. Alright, I guess they passed out. But we'll keep going just because I'm going. Alright, analyze function instructions. This looks pretty simple. We disassemble with a bunch of crap, and then we loop over these instructions and analyze them. That's cool. That means probably each instruction can be analyzed on its own. There's no like instruction sequences that are analyzed or anything. So what's disassemble? Disassemble calls the capstone library. Capstone we set up when we created our RSeq analyzer, which I kind of glossed over earlier. That called open capstone, and that configured the capstone library. What is capstone? Capstone is just a disassembler engine. It looks at machine code and lets us programmatically inspect it. You'll see more later. But when we open it up, we configure it for x86 64. So that's the... If we look at the ELF stuffs, we can see x86 64 here is the machine we're dealing with. So that's the CPU, the Intel CPU that I have. We're going to look at that kind of instruction. And we configure some options, and then we say go. And then we use that capstone handle for disassembling stuff. So to the disassemble function, we give the code, the instruction bytes of the function. So I glossed over this bit, but what we do is we take these bytes. Well, these aren't bytes. These are the assembly opcodes in text form. But the assembler will convert these into binary. So really, in the file, these are just like random, not random, but like binary things representing NOP and RET and stuff. So we take all these bytes and we hand that to the disassemble function. And we know it's these bytes because we called, what is it, function containing address, and it did the job of finding where the function starts, and it also knows the size of the function, and it called section data to pull data out of that section, out of the file. So now we have those bytes. We pass it to disassemble. We say count equals 0 because we want it to disassemble everything. And for some reason 0 means everything. You're just understanding what the things do, not all the syntax. Maybe you'll see some syntax and you'll be like, I wonder what that is. And then you'll ask about it, or you can look it up later. Or look it up now, I don't know. Did you ask about auto? Or was that somebody else? Well, yeah, feel free to ask about. Yeah, you asked about auto. Feel free to ask about other syntax stuff too. Like these comments, these are just comments. And they help me see, okay, this is the code parameter, this is the code size parameter, this is the address parameter. If this was just like a 0, I'd be like, what the heck does 0 mean? Does this mean flags? Does this mean something else? But if I see count equals 0, it's like, ah, okay. You're trying to parse no instructions, got it. Wait a minute, not no instructions. It probably means all of them. Like there's no limit. Right? Anyway, Capstone does all the heavy work of disassembling for us. And we get a bunch of objects back. We get a bunch of... let's look at the header file. Capstone. So, really what I do, I have a wrapper around Capstone. So this is the Capstone API, CS disasm, or Capstone disassemble, and we give it all this stuff. And it gives us back an array of CS instants. And what's a CS instant? It's a structure. It contains the instruction ID, it contains the instruction address, the size, the machine bytes, mnemonic, a string, and some details. So we'll take a look more into that later. So now we have an array of instructions. Let's loop over them and call analyze instruction. So here we got a CS instant, or Capstone instruction, and we got our analysis thing, which we're going to report errors to later. So this makes a local function. Let's skip over that. So we got this if. If the instruction is within the critical section. Well, that's just business logic. Let's just read the code assuming that's true or false or whatever. Written registers. Registers written by instruction. Okay, what is this? What is this doing? It's in a different file. Here we go. We got some variables we call reg's access. And we give it all these variables. We check for errors. Then we return a thingy. Basically, reg's access. Reg's access retrieve all the registers accessed by an instruction, either implicitly or explicitly. Let's look at some example instructions, shall we? Come on. Alright, let's look at some instructions. This is x86 assembly. It's not that scary. It's kind of scary. Alright, push RBP. So in this syntax, registers have a percent sign before them. That makes them easy to notice. So percent sign RBP. That means RBP is a register. Okay. Now push is either gonna do something with the register. It's gonna read it. It's gonna write it. Something. The point is, this function cares about registers written by the instruction. So if the instruction writes to RBP, then we care about it. If not, then we don't care about it. So does push writes to RBP? Well, no. It's putting RBP, the value of RBP, someplace else. It's making a copy. It's not modifying RBP. RBP stays the same as if, like, RBP doesn't change by this instruction. So it's not going to be returned. However, push has does modify a register. So in this Capstone documentation, it says registers accessed by an instruction explicitly or implicitly. So it's explicit that it does something. Push does something with RBP here. but it's implicit that push reads the stack pointer, and actually it writes to the stack pointer as well, because it needs to move, it needs to push it somewhere. Like in this push instruction modifies memory, and it needs to get the address from somewhere. So it gets it from the stack pointer, and when it's done pushing, it needs to remember that it pushed. Otherwise, you'll be like every time you push, it's going to be modifying the same memory. You want it to modify different memory so you can save all the different variables that you push, all the registers you push. So push will also write to the stack pointer. And that would be an implicit thing because it's not named in the instruction. It's just like you have to know that push modifies the stack pointer. So that's an example of what regs access would do. It would give you the list of addresses or list of registers. So for this move instruction, you'll see there's two registers being dealt with, RSP and RBP. One of these is a read, one of them is a write. It's not really important because the capstone will handle it for us. It'll give us the right answer. The move doesn't have any implicit ones. It just has explicit registers. And like, most of these things, same deal. There's a lot of explicit register use. Some of them have implicit register use. Some things like JE, they look like they don't touch registers, but they really touch the flags register because the JE needs to know the result of this comparison, or the result of this test, I guess. So, like, it can get kind of tricky for a human to think of all these cases, but Capstone handles it for us. What is in GDB? Is it an assembly language? What is in GDB? Is it an assembly? I don't know what you mean by what is in GDB. Can you rephrase the question? I'm glad you learned from Ben Eater. Those are fun videos. Anyway, back to a real world where code exists. So that's registers written by instructions. So whatever registers. So presumably somebody cares about this. What are you seeing on the screen? This is assembly code, yes. Well, disassembled. This is the output of objdump. So I ran objdump, xdr, and then the v, I ran it through vim, which is the editor with the cursor and stuff, and the colors. So we take those registers, and then we ask, did it modify a stack pointer? Which means, does it contain RSP, or if it's in the IRET group? We'll skip over the IRET group for now. We'll get into groups later. But RSP is a register, and push, so RSP is the stack pointer, so push would modify RSP, so push, like this would be true for push. But in our example, we have a NOP here, and we got NOP here. So NOP does not modify anything. It just doesn't do anything. That's what NOP means. NOP means no operation, so it ain't doing nothing. Copy all the nodes except the smallest node data in BST. Yeah, sure. Sure, I can help you out. Do you have a code snippet or something? Well, it depends on what the BST is, but Okay. Well, can you share your code and what you have so far? You could take a look. So if it does modify the stack pointer, then we report a problem. So already we have some business logic causing a legitimate error or whatever to be printed by the analyzing engine. That's all this really is doing. It's checking some random weird conditions and if on instructions, and if things don't look quite right, we report it. And we include details about it, like what function we were in and the address of that instruction. So if this push instruction was a problem, we would say address 0. I mean, or if this, let's see, if like this instruction was a problem, we would say address 13E, so that a human could go back to this output, this disassembly, and look at some information around it and maybe guess what the problem is. I would like to have line number information so you could look at your C++ code and see the line numbers, but I don't have that yet. We also include the string of the instruction, and that just uses the capstone library to get us a string, just like the string would look like this, or this, or this. Just ask capstone to do it. It can do that for us. It's got some nice helpers. Just a regular BST? Well, I would need to see your code to really help you. And to see what you tried and maybe see where your fault in understanding is or where the bug is or something. Because not all BSTs are made the same. There's many ways to write it. I mean, it might seem like there's only way to write it, but maybe that's because, like, I don't know what language you're dealing with or what. Like, there's many ways to write it, so show me how you wrote it so I can help you with how you wrote it. Okay. So if you have a GitHub account, you should share it on Gist. If not, you can throw it on Pastebin. So we include all this information in so we can print it out later. But I mean, that's just, you know, how I did it. I could have just printf, you know, right in there. But that would make it hard to test. Harder to test. Not really hard to test, but it's not what I wanted to do. Oh, well, another thing that I do is I group related problems together. So if you have a bunch of problems for the same function, then they'll be like indented and stuff like that. And if I did just printf, it'd be a bit harder to do that kind of thing. Anyway, down here we do another thing, another check. In group csgrp int, and we put that in an interrupts variable. Now this interrupts variable name gives you a hint that just like over here, modify stack pointer gives you a hint at what this means. Interrupts gives you a hint as to what csgrp int means. So let's look at csgrp int. csgrp int is all interrupt instructions, int and syscall. So if our instruction is in group, we can see in group. Whoa. In group is up here, so instruction in group. I don't know. I guess I just had a wrapper, and this just iterates over all the groups. It's kind of like registers written by instruction. It's just something in Capstone, the library. It can tell us groups of things, which is pretty handy. So we don't have to list out all of the individual instructions. We just say a group, which should be all the interrupt instructions, syscall instructions, stuff like that. And if it does do an interrupt, it is an interrupt instruction, then we also report an issue. We're reporting a different issue here, interrupt instead of stack pointer modified, so we can give a different message as to what the problem is. So this will disallow syscall. So syscall. I guess I don't have any syscalls here. Int. I guess we gotta. No, this is garbage. Well, like you can imagine a system call instruction would trigger this thing. So that's all my static analyzer is doing, is finding little patterns like this. There's a little more involved here, where we look at jump instructions, and we look at the jump target. So JE. So we had some jumps here, like JE is a jump instruction. It says jump if equal. Now we want to see if we're jumping into the wrong spot. And that's what jump target does. And we check if the address is within the critical section, and yada yada. And if so, we add a problem saying you're jumping into the critical section, you shouldn't do that. So we got a bunch of, I think that's all the assembly checks we have, really. So that's the gist of the static analyzer.